Welcome to MACSGATE. We are learning engineering mathematics through PYQs. Now, under linear algebra, the next topic is determinants. Let us consider PYQs from determinants. This question was asked in year 2001 for civil engineering student. We need to find determinant of the matrix. If you observe, none of the options are zeros. Okay? It is better to expand by any row or any column, or use row operations to make sum of the elements in a particular row or column equal to 0, then expand along that particular row. I follow the straightforward method. That is, I try to find determinant of this matrix by expanding along the first row. 5 into cofactor. 1, 1. First row, first column, cofactor sign will be positive. Remove the column, remove the row. Remaining submatrix determinant. 2 into 10, 20. 6 into 5, 30. Then first row, second column element. Cofactor sign will be minus. 3 into, remove the row, remove the column. 10 minus 18. 1, 3. Cofactor sign is positive. 2 into, remove the row, remove the column. 5 minus 6. So if you simplify, you get 5 into minus 10. This is minus 8, minus of minus plus. 8 3 is 24. And here it is minus 1, you get minus 2. So it is minus 52 plus 24 is minus 28. So the correct answer is option B. The next question was asked in year 2002 for CS student. Two statements were given. Which of the following statements is true? Whether both the statements are true, any one of them is true, or none of them is true. First statement, the sum of two singular matrices may be non-singular. He is not saying sum of two singular matrices is always non-singular. No, he is saying sum of two singular matrices may be non-singular. So for this, if you can give one such example, then it will become true. So for first statement, I just give one example. Consider this matrix. The determinant of this matrix is 0, so it is singular. Consider one more, 0, 0, 0, 1. This is also singular matrix. But sum of these two matrices is identity. And suppose let us call it as A, let us call it as B, and let us call it as I. See, det A is 0, det B is 0. But I can find in this particular situation, det A plus B, which is identity, which is not equal to 0. So sum of two singular matrices may be non-singular is true. Now second statement, sum of two non-singular matrices may be singular. See, the matrices are non-singular, but their sum may be singular. Can easily create one such example, sir. Let us try with this identity, and I take one more fellow with a small variant by making this minus 1. Obviously, if you call it as A, determinant of this is 1, which is non-zero, non-singular. B, determinant of this is minus 1, non-zero. But when you add these two fellows, you get 1, 0, 0, 0. The sum is becoming singular. That is non-inverse. So sum of two non-singular matrices may be singular, even this is true. That is, both the statements are, both S1 and S2 are. Next problem. For which value of X, this matrix is singular. So this matrix is singular means determinant of the matrix is 0. We need to find the value of. So you can expand along any row or any column to find the determinant, then equate it to 0 to find the value of X. Try to identify the row or column having more zeros and expand along that row or column. If you consider the third column is having more zeros, expand along that particular column. So what is determinant? expanding along third column. This is 0 into cofactor 0, 0 into cofactor 0. Here cofactor sign is minus, so minus 2 into, remove the row and column, 8, 6, 48 minus 12x. But determinant must be equal to 0 because it is a singular matrix. What does it mean? 48 minus 12x is equal to 0, or 12x is 48, or x value is equal. There is one more idea. See, my dear friends, whenever determinant is 0, definitely there is some relation between rows as well as columns. That is, rows are dependent and columns are also dependent. If you can able to find such relation between rows and columns, anyone, rows, if you can able to find it, using that you can find the value of x. See, for example, if you observe, half column 1 minus column 2 is column 3. Half of this, that is 6 minus 6 is 0. Half of this, 2 minus 0 is 2. So you can use that idea to get the value of x. That is half into 8 minus x equal to 0. Therefore, the value of x is equal. Whenever determinant is 0, the rows of the matrix and columns of the matrix becomes dependent. That is the trick. So the correct answer is 4. Next question, what is inverse of this 2 by 2 matrix? See, for 2 by 2 matrix, you can use the formula. Whenever it is 2 by 2 matrix, A, B, C, D, the inverse of this matrix is given by following formula. Actually, this is nothing but adjoint A by det A, but instead of writing entire story, we can remember it as a formula. This is AD minus BC, which is determinant. And for finding adjoint, just swap the main diagonal elements, change the sign of off diagonal element. So for given matrix, what is the inverse? 1 by AD, that is 7 minus 10, which is minus 3. Swap main diagonal elements, 7, 1. Change the sign of off diagonal element. Of course, you can take the minus sign inside so that it becomes 1 by 3, minus 7, 5, minus 1. So this matches with which option? Option A. So A is the correct option. Next question. Again, inverse of 2 by 2 matrix, but this time it is complex matrix. Whether it is complex or real matrix, you can use the same procedure. So this is your matrix A. So we need A inverse. 1 by AD minus BC. That is 3 plus 2i into 3 minus 2i minus I into I, that is minus I square, minus of minus plus I square. And here swap the main diagonal elements. Here you get 3 minus 2i, and here you get 3 plus 2i. Change the sign of off diagonal elements. Let us simplify. If you do not know, note it. I square is minus 1. Simplify this. Here you can use A plus B into A minus B formula. A square minus B square, that is 4I square, which is minus 4. Minus of minus plus 4. And I square is minus 1. This matrix is 3 minus 2I minus I 3 plus. When you simplify, you get 1 by 12. 3 minus 2I minus I plus. So the solution is option. Next question. Which of the following does not equal to determinant of this matrix? There are 4 options. Dear friends, if you consider your original matrix, it mainly depends on observation. 1, 1, 1, x, y, z, x square, y square, z square. See, actually, I want to get option A. If you actually observe this option A, it is, if you expand, it is x square plus x. y square plus y, z square plus z. See, this is obtained by adding these elements. So what we are doing, column 3 is column 3 plus column 2, and it will not change determinant. So first column remains as it is, second column remains as it is, third column is x square plus x, that I can write it as x into x plus 1, y square plus y, I can write it as y into y plus 1, z square plus z, that I can write it as z into z plus 1. Now again what I do, column 2 is column 2 plus column 1. First column remains same, but second column changes as x plus 1, y plus 1, z plus 1, and this is x into x plus 1, y into y plus 1, z into z plus 1. But if you observe option A, and these two columns were interchanged. But if you interchange columns, the determinant sign will change. So suppose if this answer is say k, this is obtained by interchanging columns, this answer would be minus k. So this fellow cannot be equal to option E. So this determinant cannot be equal to this particular determinant which is given in option A. So this is the correct answer, because he is asking which of the following is not equal to that. So option A is the answer. So you got answer readily. Let us see how B, C, D are equivalent to the determinant of the given matrix. See, if you actually observe B option, it is actually obtained by what method, sir? You are doing x plus 1, y plus 1, z plus 1, and it is obtained by x square plus 1, y square plus 1, z square plus 1. So from the given matrix, you can easily obtain, sir. Suppose if given matrix is this 1, 1, 1, x, y, g, x square, y square, z square. So you can just do column. Okay, here it is about columns. So let us do column operations. Column 2 is column 2 plus column 1. You will get this. Then column 3 is again column 3 plus column 1. You get this. So both are equal. So given determinant equal to this particular determinant given in option B. Let us check option C. See, this is very interesting. See, this is the matrix. What we can do is, see, if you observe, it is x minus y. X minus y, x square minus y square means this one. So first of all, we are doing this operation, that is R1 is R1 minus R2. See, these are two separate operations. So here you get 0, x minus y, x square minus y square, and this is as it is. In the next step, you want y minus z, no? Then you can do R2 is R2 minus R3. See, these two row operations need to be performed separately. You cannot do it at a time. You cannot do it at a time, remember. That is the trick in this particular problem, sir. So 0, x minus y, x square minus y square. Here 1 minus 1 is 0, y minus g, and y square minus g. And this is 1 g square. That is the logic. So the given determinant equal to determinant given in option C. What about D option? See, for D option, I'll just give you the logic and try to verify yourself. See, by observation, you can solve such problems, my dear friends. Here you want 2 and x plus y. X plus y means this sum. X square plus y square means this sum. So first you have to do the operation row 1 is row 1 plus row 2. After getting the answer, that is 2x plus y, x square plus y square. Then it is 1y, y square. It is 1z, z square. Then you have to do the next operation to make it 2. That is R2 is R2 plus R3. So you get the required answer. So the given determinant is also equivalent to determinant given in option D. So which of the following does not equal to determinant? Option A. Next question. See, ultimately is asking you to find determinant of this matrix in this problem. But here he given a hint. Of course, in the examination, if you want to use the hint, you can use it. Otherwise, you can solve by your own methods. There are multiple ways of solving this problem, sir. Even using eigenvalues, eigenvectors, you can solve it. But let us try by the method which he want you to solve it. Okay. So that is what I am trying to do now. See, what he mentioned is, this is the matrix A, and okay, let A be m by n matrix. Okay, and B is n by m matrix, and it is given that we have such a relation. Okay, Im plus A into B is equal to, that is determinant of this matrix, is equal to In, determinant of In plus Ba, where Ik is K by K identity matrix. Using the above property, using this property, you have to find determinant of this matrix. Of course, this is not the matrix A, sorry for that. It is not the matrix A. So using this property, you have to find the determinant of this. Of course, for university examination, you have to use the property. In GATE, you can directly try by other methods. Okay, but let us use the same method. So what I do is, this matrix, I try to write it as identity plus something. See, if you want to write it as identity plus something, 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, the remaining matrix would be what, sir? Obviously, because only main diagonal elements are 2, means from main diagonal you are removing 1. So what happens? What is remaining? 1 is gone, means 1 more. That is, you can write 2 as 1 plus 1. So what is remaining? 1. Remaining elements are not changed. Here also 1 is used here, the other one is here. Here also 1 is used here, the other one is here. Remaining elements as it is. Here also 1 is used here, the other one is here. I mean here. So the given matrix can be written as I4 plus this matrix is our A. So suppose if you call it as some P, the determinant of this is equal to this one. Now if you observe, A is m by n. So here A matrix is 4 by n and B matrix is n by 4. See, you have to find a n value such that this condition is satisfied. There is no restriction. You can't take this value or that value. You can try anything, sir. This is open. So what I do is, I take n is equal to 1. So A becomes 4 by 1 and B becomes 1 by 4. I'm just trying, sir. I'm just trying with n is equal to 1. See, I can get such a matrix very easily, sir. 4 by 1 means if I take all ones, and B if I take all ones, this fellow 4 by 1 into 1 by 4 will become 4 by 4. So I can get this AB by this method. I can get AB by this method, where A is all ones and 4 by 1 matrix, B is all ones, 1 by 4 matrix. Now what he says, this fellow is equal to In plus Ba. This determinant is equal to determinant of In plus Ba. But n is equal to 1 means what is In? It is I1. That is single element. Now if you consider Ba, what is Ba? Ba is 1 by 4 and A is 4 by 1. It is also 1 by 1 matrix. And what is it, sir? It is 1, 1, 1, 1 and it is 1, 1, 1, 1. And what is Ba, sir? It is a single element. So determinant of this matrix is equal to determinant of this. Now what is this I? I1. It becomes I1. And what is Ba? Ba is a single matrix 1. So sum of these matrices, determinant is your answer. And what is I1 plus? See, this is 1 plus 4, sir. It is simply matrix 5. And you need determinant of it. Of course, when it is a matrix, you don't need to write all that, sir. Simply you can write det 5. And det 5 is 5. So determinant of this matrix is 5. Using the procedure which he asked. See, otherwise you can use multiple methods, sir. You can do one thing, like, R1 is R1 plus R2 plus R3 plus R4. With that, what happens? You get 5. So you can take 5 common. You get all ones here. Then you can try to make these fellows 0 using this. Then it reduces to some simplified matrix and you can expand along first row. You can get the determinant. Of course, I am not interested in that. I just want to apply the method which he gives. So the answer for this problem is 5. 5 is the answer. That is option B. Next problem. What is determinant of this 4 by 4 matrix? See, actually, it is a symmetric matrix. For symmetric matrix, we don't have any special method, my dear friends. Only thing is A transpose becomes A. So determinant of A and determinant of A transpose are same. Of course, that properties does not work here. So what we do is, let us try to expand along any row or any column. Try to identify the row or column having more number of zeros. If you observe, second row or second column having more number of zeros, 2 zeros. If you want, you can make one more fellow also 0. Try to make this 0. So this column contains 3 zeros. So we can expand along that particular column. So let us try that. That is, what I do is R3 is R3 minus 3 times R1. So by this, determinant will not change. So when you want to find determinant, if you do strictly third type of row operation, determinant will not change. First row as it is, second row as it is, third row. So what you are doing? 2 minus 3 times 0, that is 2 only. 3 minus 3, 0 minus 6, and it is 1 minus 9, which is minus 8. Remaining fellows as it is. So I created more number of zeros in this particular column. So expand along this particular column. So what happens? The determinant of the matrix is, because it is first row second column element, 1 into minus sign. So minus 1 into, remove the column and remove the row, remaining submatrix determinant. What is remaining submatrix determinant? So when you remove the column and row, what is the remaining submatrix? 1, 3, 0, 2 minus 6 minus 8, 3, 1, 2. We need to expand this 3 by 3 determinant, my dear friends. And try the same method. Okay. Let me expand along the first. So it is minus of, so what happens? Let us see. 1 into minus 12 plus 8. Minus 12 plus 8 is minus 4. Minus 3 into 4 plus 24. 28. So what you are going to get? Minus, this is minus 4, 60, 84. It is minus 80. So we are going to get minus 88, minus of minus plus 8. So the answer for this problem is plus 8. Next question. Determinant of A is given. Determinant of B is given. What is determinant of AB? See, it is a Lilliput question, but if you don't know the property, it is a very dangerous question. You know det AB is equal to det A into det B. So that is 5 into 40 is 200. Next question. Matrix A is given as product of these two matrices. What is determinant of A equal? Here friends, if you observe, it is a 3 by 1 matrix and it is 1 by 3 matrix. Actually, when you multiply, what happens is, this 2 will be multiplied with every element. So if you call it as some row, you just call it as some R. So the matrix which you get is 2 times of R, minus 4 times of R, 7 times of R. So these are the rows. But all these rows are proportional, because you can see that, okay, this is row 2 now. Row 2 is equal to minus 2 times row 1. Because rows are dependent or proportional, the determinant of this matrix will be obviously. So without writing complete expansion, you can directly by observation solve the problem. So the answer for this problem is 0. Perform the following operations on the matrix. This matrix is given and he is asking you to perform the following operations. Then the determinant of the resultant matrix. What operation is performing? Let us see. Add third row to the second row. That is, row 2 is row 2 plus row 3. Second operation. Subtract third column from first column. That is, third column need to be subtracted from first column. You are going to get column 1. But these are third row and third column operations, these operations do not change determinant of the matrix. See, some people directly start applying these operations, my dear friends, but try to understand what these operations are doing. See, even if you perform these operations, determinant is not going to change. So the resultant matrix, whatever you call it as B, suppose if it is called as A, it is called as B, the determinant of B is exactly same as determinant of A. So just find determinant of A, you will get the answer. And if you observe matrix A, 15 times of column 1 is equal to column 3. 15 3 is 45, 15 7 is 105, 15 13 is 195. Because of this, the determinant of A becomes 0. Therefore, determinant of B. So, solution for this problem is, next problem. Here matrix A is given. He is asking you to find determinant of A transpose into A inverse. See, we need to find determinant of A transpose into A inverse. So, generally what people do, they find A transpose, they find A inverse, multiply, then find determinant of the matrix. I also find this solution in some of the PYQ books. Dear friends, we know this property det AB is equal to det A into det B. So, determinant of A transpose into A inverse is det A transpose into det A inverse. But det A transpose is same as det A. Det A inverse is 1 by det A. Now here, if you want to write this, you have to prove that det A is not equal to 0. Now whether it is correct or not. For that we make use of matrix. Some people say matrix is useless fellow here. No, matrix is needed because you need to check whether det A is not equal to 0 or not. Then only you can apply this. Otherwise this problem has no solution. Note that because A inverse does not exist, then how can you multiply A transpose with A inverse? So for that we need to find det A. What is det A, my dear friends? Which is 1 plus tan square x. See, tan square x is positive, 1 is non-zero. So 1 plus some positive value will be definitely non-zero. So det A is definitely non-zero. Yes, it is. So I can write like this. These two get cancelled. The answer 1. So the correct answer for this problem is 1, which is option C. Next problem. Again 4 by 4 matrix is given. He says determinant of this matrix is 100. Trace of this matrix. What is trace of the matrix, my dear friends? Which is sum of main diagonal elements. That is A plus 5 plus 2 plus B. And he given that trace is equal to 4. Means what? A plus B plus 7 is equal to 14. Therefore, A plus B is equal to 14 minus 7. That is 7. So, you got one relation. Next, determinant is equal to 100. How to find determinant of this matrix, my dear friends? See, actually, if you observe, it is block diagonal matrix. So, you can use this. Here, PQRS, R is 0. So, what is determinant of A? You can easily find determinant of A as determinant of this P, that is A0, 2, 5, and determinant of this S, which is 2, 4, 0. And this determinant is simply 5A, and this determinant is simply 2. So, the product is 10, but it is given as 100. So, we get AB is equal to 100 by 10, which is 10. So, you got the relation between AB, two relations. You need to solve the two relations to get AB values, then find mod A minus B. Or from your elementary mathematics, you all know A minus B whole square is equal to A plus B whole square minus 4AB. Remember this? So A plus B whole square means 7 square minus 4 into AB is 10. 49 minus 40, that is 9. So A minus B whole square is equal to 9 means mod A minus B will be positive square root of 9, which is. So the answer for this problem is, so 3 is the correct answer. Next problem, he given a 6 by 6 matrix, okay, which is obtained by reversing the orders of columns of identity matrix. Now there is a matrix P which is defined as I6, 6 by 6 identity matrix plus alpha times J6. If determinant of P is equal to 0, we need to find alpha value, and it says that alpha is a non-negative real number. Alpha is a non-negative real number. See, one method for solving this problem is observation method. Otherwise, people try to take 2 by 2 matrix, then 4 by 4 matrix, then they try to find some relationship, they generalize it, from that they try to find alpha value. But I suggest this simple observational technique for this problem, my dear friend. So actually, if you observe this P, which is actually P is I6 plus alpha times J6, what happens here? Identity means the main diagonals will be 1, and alpha times J6 means this reverse diagonal elements will become alphas. So what actually you get is 1 0 0 0 0 alpha, then it is 0 1 0 0 alpha 0, then 0 0 1 alpha, then next one is 0 0 alpha 1 0 alpha 0 0 1 0, finally alpha 0 0. Now dear friends, he says determinant of this fellow is 0. See, if you observe the first and sixth rows, the first and sixth rows, if you observe, see, when determinant is 0, definitely there will be some relation between rows. Of course, relation may be existing between, okay, many rows. That is, the rows becomes linearly dependent. Actually, only here we have non-zero elements. So only we should have some relation between these two elements. Now if I make alpha is equal to 1, determinant becomes 0 or not. So definitely I can consider alpha is equal to 1. Definitely I can consider alpha is equal to 1. Actually alpha is equal to minus 1 also I can consider. Then what happens? This becomes 1 0 0 0 minus 1, and it becomes minus 1 0 0 0 0 1. So these two rows becomes proportional even in this case, but you need only a non-negative real number. Therefore this alpha minus 1 will skip. We take alpha is equal. The other method which people try is the following. They start with a 2 by 2 matrix. For 2 by 2 matrix they find a relation, they generalize for 6 by 6 matrix. Like, you know, when you consider 2 by 2 matrix or 2 by 2 variant of this, you get something like 1 alpha alpha 1. This must be equal to 0, means 1 minus alpha square is equal to 0. This is for 2 by 2 matrix. Then they try it for 4 by 4 matrix, and they prove that for 4 by 4 matrix it is 1 minus alpha square whole square. So similarly for 6 by 6 matrix they say the relation is 1 minus alpha square whole cube is equal to 0. Whatever it is, the answer for this is 1 minus alpha square is equal to 0. That means alpha is equal to plus minus 1. You cannot take negative value because you require only non-negative real number. So alpha is equal. This is other method which people follow, but I suggest this observational method. Definitely this value of alpha can be taken, because by taking alpha is equal to 1, first and sixth rows becomes equal, determinant is 0. So this value of alpha definitely makes determinant equal to 0. I can consider that particular value of alpha. No one can deny. So that is the answer for this problem. Okay. So what is the answer? Alpha value is 1. So these are some problems from determinant, my dear friends.